Everyone, thank you very much for joining iNEMI Package Tech webinars. My name is Surias from iNEMI. And today's topic is challenges and equipment solutions to enable next generation electronic systems using hybrid bondings, presented by Chris Scanlan from Besi. Let me briefly introduce today's presenters. Chris Scanlan. He is the Senior Vice President from Besi, and he's leading the advanced technology roadmap development and technical promotions. Abstract. Chiplet architectures and advanced SiP devices requires integrations of multiple chips with advanced fine pitch interfaces. Chip-to-wafers hybrid bonding is a new interconnections technologies that provides extremely high interconnect densities like a chiplet. Chris will discuss some of the challenges and equipment solutions to enable next generation's electronic systems using hybrid bonding. This Package Tech webinars is organized by iNEMI Package Technology Group, chaired by Dr. Wei-Ki Lo from Intel. And he will list the Q&A sessions later on. And we will organize the webinars next year as well. So please visit iNEMI website for further schedules. Okay. And please mute your lines during the presentations. And as I mentioned, that we will send the email with download link next week, so you can get the presentations copies from the link. Okay, Chris, shall we start? Would you please start?
Yes, Surya-san, thank you very much. Can you hear me well?
Yes, thank you.
Okay, let me try to share from my side.
Okay.
Let's see. That's not it. Okay. I think I have the proper file. Please let me know, Surya-san, if you're seeing this okay.
Yes, good. Thank you.
Okay. Surya-san and the iNEMI team and everybody online, thank you very much for your time and attention today. It's a really great pleasure to be able to talk to all of you, especially about some of the really exciting new interconnect developments that we're working on here at Besi, along with some industry partners as well. As Surya-san already mentioned, I'm SVP of Technology at Besi. I've been with Besi for about 2 years, working in the CTO office here at Besi. I'm based in Switzerland, where we have the headquarters of our die-attach business unit. I'm currently sitting at the Besi headquarters in the Netherlands, talking to you from here. Prior to joining Besi, I was for about 20 years or so in the OSAT side of the semiconductor business. So that's outsourced assembly and test type companies. And then starting out at Motorola Semiconductor, where Grace and I knew each other a little bit back then. So I'll talk to you about assembly technologies for next generation systems. I'll focus mostly on hybrid, but I'd like to also talk a little bit about other chip to wafer type assembly technologies that are needed to complement hybrid bonding for a lot of these new chiplet architectures that we're seeing. I just need to remind you, this is Besi's a public company traded here in the Netherlands, so please don't trade based on what I tell you today. Just to introduce Besi a little bit. So some of you may be aware or familiar with some of the brands that Besi's acquired and integrated over the years, including Datacon, ESIC, FICO, for example. But we're a leading provider of assembly equipment for the back end of the semiconductor industry primarily, where we have leadership positions in die attach and also packaging and plating. We have about 2,000 employees, most of them in Asia, and revenue of about 750 million euro on an annual basis. Our product portfolio is really focused on advanced interconnect, including die bonding, various types of flip chip and multi-module attach, and then advanced chip to wafer assembly, which we'll focus on for the talk today, as well as packaging and plating type equipment like molding, trim and form, and singulation. Our direct customers are typically, all the big IDMs, OSATs, and system companies in the world. We've been around a long time, and we've worked and are working with most of the big companies. Our headquarters is here in Duiven, Netherlands. That's where I'm located right now. We also have the R&D center for our packaging business unit, which is the FICO branded business unit. Also in the Netherlands, we have a plating business unit. And then in Switzerland and Radfeld, we have the R&D centers for our die attach business unit. So in Switzerland, we're focused on die bonding and soft solder type equipment. And in Radfeld, Austria, which is in the Tyrol region of Austria, we're focused on advanced flip chip, multi-module attach, and things like hybrid bonding and TCB. So all of our R&D is really done in Europe. The advanced R&D, we have an application and support center in Singapore as well. We do some evolutionary development as well in Singapore. And our main production sites are in Malaysia, near Kuala Lumpur, as well as in Lishan, China. Recently, we've also expanded to set up application laboratories in Taiwan and now in the US as well. A little bit more detail on the product portfolio. Today, we'll talk quite a bit about hybrid bonding. We have introduced about a year ago a new platform for hybrid bonding focused on chip to wafer hybrid bonding for logic and memory. We've also been in development with a thermocompression bonding system, which I'll talk about, and a new platform for embedded bridge attach and basically fan out kind of applications. We're the market leader in high performance flip chip and high speed flip chip equipment. We also have custom direct lid attach equipment. This is to mount the thermal lid on the back of high performance flip chip packages. And then our epoxy and soft solder machine, the 2100 family, is really focused on strip-based lead frame and strip-based substrate, die attach and flip chip attach, as well as soft solder die attach. And then finally, the multi-module attach is a very flexible system that can do things like camera module assemblies, very large die size flip chip attach like interposer attach, and a variety of other processes. And then in the packaging and plating product lines, we're offering wafer level molding, which I'll talk a little bit about, as well as substrate based molding. This is all transfer molding and lead frame molding. And associated with that, we also perform the final step, which is singulation or trim and form in the case of lead frame. And then finally, we have a business unit here in the Netherlands that is supporting plating primarily for lead frames. So plating the tin or the final surface finish on the lead frames. So that's a little bit about Besi. Now I want to turn my focus here in the talk to what's happening in our industry. And yeah, I'd like to start with this chart from SEMI. This is recently published, I think about 6 months ago. SEMI updated their long-term forecast for the semiconductor industry. And Yeah, to me, it's just simply interesting because I got my start close to the beginning of the chart here in about 1994. I graduated from college and got my first job at Motorola. And at that point, I think the revenue was about 140 billion. That was the total revenue of the semiconductor industry. And we were really in the PC era at that time. When I arrived at Motorola, they gave me a pager. We didn't have cell phones. Really, nobody even really had pagers except doctors and lawyers. Um, but anyway, that's kind of where I'm coming from, my perspective on the industry. And I've really kind of observed the growth of the industry through this very stable sort of era where we made the transition into mobility. The cell phone became ubiquitous. But all through this era, we had, really this trend of Moore's law uh, supporting cost reduction and production ramp, allowing us to continuously shrink the die. Every generation, we could shrink the die and at the same time integrate more functionality on the die, more transistors on the die to create these fantastic new products. But we really weren't increasing the costs that much in relation to the functionality we were adding, simply because Moore's law allowed us to move down the cost curve at the same time. Now we've kind of moved into the big data and AI era, and I'll talk a little bit about that on the next slide, but there's something that's changed in the last 10 years, and you can see that semi's forecasting a much steeper ramp in terms of revenue going forward to the point that we'll surpass $1 billion or $1 trillion in revenue by 2030. They're actually forecasting something like 1.3. But what's changed, and I would submit that there's really two things. The first thing is that back in this era, at the beginning and through the cell phone era, was really we humans that were creating most of the data, most of the information that we had to process. But now we've moved into an era where our machines are doing that for us. So we're automating the process of creating data. So we have basically robots or machines that are creating this huge volume of data. It's not limited by our human energy anymore. And that's simply creating more information that has to be processed and stored and computed. The second thing is that transistors are not shrinking. So in order to continuously increase the functionality of our devices, we simply need more silicon area, and that silicon area costs more. And so we're losing the ability to keep on this very flat cost curve. And that's those two things together, I think, are driving this overall trend. And here you can see in a little bit more detail, some evidence that we're moving into this computing era and away from the reliance on mobility. You see on the left the rapid expansion in cloud computing infrastructure. In recent quarters, this has kind of tapered off a little bit, but it's been a very rapid growth. And on the right side, you see some data from IDC. This is showing the percentage of revenue from different types of end applications for the foundry business. This is the TSMCs and Global Foundries, those kind of companies. And what you see is that in 2021, there was a transition where now HPC is basically overtaking mobile as the largest percentage of revenue. And that is expected to expand over time. And that's simply because we've moved now into this cloud-based computing era. And this in turn is really driving the need for chiplets. And why chiplets? So the other issue, or the fundamental issue, I guess, that the industry is facing is how to scale transistors and how to scale devices. So we've already moved into kind of this era of, I would say, 3D integration on the front end. So for the first 40 years or so of our industry, we were just kind of shrinking geometries. We made some changes to the architecture of the transistor, but fundamentally we were just year on year able to shrink the geometry through process development in the front end and simply fit more transistors on a silicon wafer. And already about 10 or 15 years ago, we had to start to go 3D. So we started with the FinFET. We started with this idea of a vertical structure in our transistors, and now we're seeing the introduction of nanosheets, or there's various different names for this, but this is basically a 3D integration on the front end. And remember, all this takes more time and process steps in the front end as well, which all adds cost. And in the future, we're looking at even more exotic structures, or even going to three-dimensional transistor stacking on the front end. So this is all happening. Our colleagues on the front end haven't given up on Moore's law, but they're on the right. You can see that the result of this is that we're having challenges to scale the transistor energy efficient performance. So this is the amount of energy it takes to flip a bit isn't scaling along with the progression of nodes as fast as it used to. So all this together means that we're not shrinking the chip as much as we used to for a given increase in functionality. And yeah, just another way to look at it from AMD, they're showing evidence of this. You can see that as we've gone from the 28 nanometer node to down to now 5 or 3 nanometer, we've been able to scale logic. This is the actual logic transistors, but other kinds of functions in the silicon device are not scaling. So SRAM faces limitations. So as we shrink a device that has half of the device area in SRAM or analog, it's just no longer shrinking. We shrink the small portion that is still logic, but the rest of the device is not shrinking. So the die become bigger. So the end result is that we have to go to chiplets. And chiplets are, of course, the concept of taking what used to be a monolithic system on chip device with a whole bunch of different functional blocks integrated together on a single process node in the front end, to a new architecture where we're splitting those functional blocks into many different tiles or chiplets, and then integrating together in a package. This allows us to increase the total yield of the system because we can make each of these individual chips smaller and therefore higher yielding in the front end. And also provides the ability to mix and match different process nodes and optimize different features or different functions with the appropriate node, and also optimize capacity in the front end. So there's a lot of benefits to this. This is one example from Intel that you see here. This is the famous Ponte Vecchio. Many people have seen this, of course, but it's an example of a chiplet architecture with 47 chiplets in one package, 47 slices of silicon. And when you look at these really complex packages, I made this kind of cartoon just to kind of communicate what do you see inside these things really. And today we'll talk a little bit about hybrid bonding. Hybrid bonding is the most advanced interconnect that allows very fine pitch direct interconnection between the back end of line buildup layers on a silicon device to a similar back end of line or TSV structure on another device, so allowing you to make very low impedance contacts and very high density, high bandwidth contacts between chips. And this really allows designers to design in 3 dimensions without implementing energy sucking IO buffers and things like that between the chips. It's really a direct connection. So this is the most advanced interconnect that you might find in some of these chiplet systems. But it's important to point out that even if you have hybrid bonding, you still have to get, at some point, those signals out to other functional blocks in the system. And that requires typically some kind of flip chip interconnection on at least one side of this hybrid bonded chiplet stack. Typically that flip chip connection will be to some kind of an interposer, either a functional die like Foveros, like a functional silicon interposer, or it could be any other kind of interposer. It could be a glass interposer, it could be an epoxy interposer with embedded bridge die. A lot of different possibilities. But typically you'll have your hybrid bonded chiplets co-located on this interposer with other types of chiplets and other types of 3D stacks of memory or other functions. Could even be optical chiplets, for example. And then these interposers are typically encapsulated, tested, and then further assembled onto a very large package substrate. Maybe integrated with other kinds of chips on the side as well. So these things become very complex, and within these structures you have the need for multiple different kinds of interconnects. You have hybrid bonding, you could have chip to wafer TCB for the hybrid bond stack attached to the interposer or the other chiplets, or even for the high bandwidth memory stacking. Hybrid bonding itself can be used in this area as well. And then you have the whole problem of how to integrate bridge die. These are local silicon interconnects that are sort of embedded in the interposer, either the high density interposer or the package substrate itself. And then all this needs to be encapsulated. So these are really complex systems. What we're doing at Besi, our focus is to really provide all of the technology that you need to create all of these interconnections for these high performance computing applications. But I want to focus first on hybrid bonding, since I think that's a hot topic. Where does hybrid bonding come in from a roadmap perspective? Really it's the most advanced interconnect that we have in our portfolio. So today we can get our flip chip, our standard flip chip mass reflow, down to a pretty aggressive pitch for this technology, 16 micron pitch. If you're assembling onto a very flat wafer, maybe down to a little bit below 40 micron pitch. We have thermal compression capabilities as well. So with thermal compression, you can achieve a slightly more aggressive pitch. With chip to wafer thermal compression, we think get down to maybe 15 to 18 microns is kind of the practical limit. Below that, you start to run out of volume of solder in order to make a reliable connection, even if you can make the initial connection. So we think that's about the practical limit there. We have partnerships with organizations like iMEC, looking at technologies like insertion bonding. Basically methods of using the thermal compression equipment platform, but using more exotic sort of bumps, let's say it that way, to create even finer pitch interconnects. But even then, we think we're limited to maybe 10 micron or a little below. So really below about, this 18 micron limit for thermal compression with micro bump, you really have to go to a copper-copper interconnect. And when you go below about 10 micron, we think hybrid bonding is the most appropriate way to do that, because you take advantage of the direct connection between the back end of line structures on each chip. So how does hybrid bonding work exactly? So this is kind of a high level view of how hybrid bonding works conceptually. So why is it called hybrid bonding for starters, right? So hybrid bonding is the bonding of two different kinds of materials in a coplanar kind of interconnect. So there's a first bond between passivation layers or oxide layers on the device die and the substrate wafer, as well as the copper interconnects on both sides as well. So there's three basic kind of process modules that are required in order to achieve a hybrid bond. The first is the surface preparation. So in this phase, what we do is we prepare the the bonding surfaces on both sides and the device die as well as on the substrate wafer by planarizing. So we need a very perfectly flat passivation structure because these are not compliant materials. They're very hard and non-compliant. So we have to have almost perfectly flat structures there. And in addition, we need to have the copper ever so slightly recessed below the surface of the passivation so that we can make the first contact during bonding between the passivation layers and not between copper layers. That's called dishing. You might hear this word dishing. So once we achieve that very flat surface and the dished copper, then we have to activate the surface. So for this, we're typically using some kind of a plasma to create an activated oxide surface so that we have an attraction when these two surfaces meet and kind of a spontaneous bonding. So there's a lot of technology involved in creating this optimum structure, the material selection of the oxide and so on. A lot of discussion about nanotwinned copper and different kind of microstructures for the copper. I'm not going to talk about those things in detail in this discussion. The next step is die to wafer bonding. This is where Besi is really most closely involved. So we make the equipment that does this part of the process. And in die to wafer bonding, we first precisely align the device die to the substrate wafer. And we bring the die in contact to the substrate wafer. And when we do that, there's an instant bonding between these oxide activated surfaces. We can achieve that with very low force, typically. So in the range of maybe 10 to 15 newtons, and a very fast time. And we do this as well at room temperature. It's not a process that requires any heat. So it's really relying on the activation of the surfaces, the flatness of the surfaces, and the geometry. But remember, these are very, as I said earlier, very high modulus, very hard materials. So any small particle that exists in this interface during bonding will actually kill this joint. So we cannot tolerate any even 100 nanometer size particle in this interface. Therefore, the equipment design and the operation of the fab and the integration with the upstream equipment is incredibly critical in order to create a front-end type cleanliness level to achieve this process with high yield. After we create this oxide bond, then we go through an annealing step, and I'll give you a little bit more detail on that here in this slide. So typically we do this annealing in two steps. We have a first step wherein we ramp up to a lower temperature in the range of 150 C, for example. And during this part of the process, we're creating a interdiffusion of the oxide layers. Initially in the bonding process, they're stuck together basically with van der Waals forces, but in this annealing step, we're actually causing interdiffusion to occur. And then once that's had a chance to stabilize and we've strengthened the interface here so that it's rigidly attached, then we heat up the copper, the whole system even more. The metal expands and makes contact, and we have interdiffusion. And this is where the microstructure of the copper, the orientation of the grains, the size of the grains, all that stuff is really important in order to optimize this process. You can modulate the temperature that you need in order to achieve this interdiffusion. In some cases, for example, for memory devices, it may be desirable to achieve this annealing at a lower temperature to protect the integrity of the memory. Some of that can be done by, careful deposition of the copper to control the grain structure of the copper. But in any event, it's typically this kind of a two-step process that we do in order to achieve that annealing. And then this next slide is talking about some of the first applications that we're seeing in the market for chip to wafer hybrid bonding. So as many of you know, hybrid bonding itself isn't really a new technology. It's been available on a wafer to wafer level for many years. So, people are using it for things like image sensor assembly, and other kinds of applications where you can have the same die size on both wafers and then simulate a stack of devices after bonding. Typically that requires that you have, as in an image sensor, for example, one maybe high value, perhaps even lower yielding device combined with one or more chips that are very high yielding and low cost, and also the same size. So that in those applications, another example of that might be, integrating decoupling capacitors, or wafer with an integrated passive network onto the back of a logic device. Things like that, where you have a low cost, high yielding wafer that you can bond to a high value device wafer. Again, with devices being the same size, wafer to wafer bonding is used, has been used, and will be used in the future. Where die to wafer hybrid bonding comes in is in those cases where you need to integrate devices that are of different form factors. Maybe a smaller device on top of a larger device, or when you have multiple devices, all of which or some of which are higher value, perhaps lower yielding, where you need the ability to probe and sort devices before integrating them together in the stack. That's where die to wafer hybrid bonding is finding applications. In this application I'm showing you here is the first real high volume application of die to wafer hybrid bonding. This is from AMD. They've announced over a year ago already. This is their compute tile in their new chiplet architecture for their EPYC family of CPUs. And what they're doing in this case is they have, let me turn on my pointer. Yeah, so in this case, what they are doing is, and of course this is an artist rendition, this is not exactly how the devices look, but in any event, the bottom die is a compute tile, so it contains 8 CPU cores, 4 on the left and 4 on the right. And then in the center of this base tile is SRAM. That's so far pretty typical for a CPU. You have some kind of combination of CPU cores and embedded memory for L2, L3 cache. What they're doing differently here is this base tile has been designed specifically to accept another layer of memory that is integrated using hybrid bonding in a face-to-back kind of an assembly process, meaning the face of the memory device on top is attached to the back side of this logic device. So the logic device has through silicon vias, and then on the back of the TSV structure, they have formed hybrid bonding bond pads and another oxidation layer to prepare the surface for hybrid bonding. And then these memory devices are attached to the back of the CPU device. This memory device is smaller compared to the logic device here. And on either side, also mounted to the memory device or to the logic device, are blank silicon strips, effectively. These are structural silicon. They don't have any electrical functionality, but they play 2 important roles in the assembly of this product and the function of the product. One is they simply provide structural support during the subsequent processing of this product. And the second thing is it provides a thermal path for heat coming from the CPU cores to be extracted from the back of the stack. So they don't have to go through this memory, they go directly through this structural silicon and can be kind of the heat can be extracted from another layer of material mounted to the back of this whole assembly. On the bottom of this thing is a flip chip interconnect. So everything I just described is a quite complex hybrid bonding assembly, but on the very bottom of this thing, you can see on the substrate here, they assemble actually these tiles after the hybrid bonding is done using flip chip bumps to the package substrate. So as I mentioned, anytime you do hybrid bonding in these kind of systems, you typically need to combine that with some kind of a flip chip interconnect because you have to eventually make connection to the package substrate. The interesting thing about these products is the flexibility that they've demonstrated in terms of configuring different kinds of products using the same chiplet in combination with different kinds of I/O chips and different numbers of these tiles. That can optimize these systems for different purposes. So this EPIC Milan X, for example, was really optimized for EDA kind of applications. So high-end workstations that are maybe doing chip design. And this Ryzen 7 really optimized for gaming. So you can see a single CPU die instead of 8 in combination with a different I/O die. But yeah, this really kind of demonstrates the flexibility of this chiplet architecture to mix and match functions in different die using standardized functional blocks to create different kinds of optimized systems. Okay. Yeah, just some more detail on what this looks like. This is data from Yole, and you can see here the more detail on the assembly of the chiplet. You can see the very thin chiplets that are stacked on top of each other using hybrid bonding, and then the flip chip interconnect that is used to mount these things to the package substrate at the bottom. And this is a more of a close-up view of what the hybrid bond looks like after bonding. You can see, the through silicon vias here on the back. This is the compute tile. So you can see the transistors, the back-end line routing, and then the TSV connecting to kind of the via middle structure through the back of the die. The hybrid bond pad that's formed on the back of the die with an oxide layer there. And then the top die with a copper via through the passivation. This is a very thick passivation with a little bit smaller hybrid bond pad, copper bond pad. You can see that they're connected with very precise bonding. I would estimate this is less than 100 nanometer misplacement in this particular image. You can see a little bit more detail on this side. So this is about, you can see from the scale here, this is 3 micron. The bond pad is roughly that dimension on the bottom side and a little bit smaller on the top side. And it's pretty well centered in bonding. Yeah, and you can kind of see the very complex sort of build-up structures and the oxide layers and multiple different materials used. But yeah, this is really in high volume production now. You can go out and buy this and cross-section it yourself if you like. So where do we see hybrid bonding going? So I just presented an application for logic, and we definitely see logic as the leading application for die-to-wafer hybrid bonding. We've seen other companies like Intel announce plans and announce architectures that they're working on that really require 3 micron interconnect pitch. So more logic devices will be coming to market in the coming quarters. We also see that memory is an application that could use hybrid bonding in the future, specifically high bandwidth memory. So high bandwidth memory is already leveraging advanced thermocompression bonding or mass reflow. But today's high bandwidth memory, HBM3 has just come to market with up to 12 die stacked, 12 memory die on top of a logic device. And with HBM4, we anticipate 16 to 20 devices will be integrated vertically. And as you go to 16 devices, you simply kind of run out of space because this whole HBM stack has to be at least thinner than the logic device sitting next to it. That's because you need to create a good thermal interface to the logic device and to the memory device. So you can't have a very thick memory device. So therefore, once we go to 16 die stack, we think just from a height perspective, as well as a thermal performance perspective, we'll need to go to hybrid bonding. And in the mobile space, we see potential applications, both in the application processor as well as in the RF section. And then also in a variety of sensor to display, and I would say optoelectronic applications where you might use this concept of fusion bonding, or the fusion bonding is basically the hybrid bonding without copper. There's many applications where that could be utilized with high precision bonding. So this is where we see some of the future applications. And with respect to the application processor for cell phones, we think that's a logical next application for hybrid bonding. Of course, we don't know when that will actually happen, but if you simply look at the number of transistors that are being integrated and how that's growing year on year in these application processors, and the additional functionality like AI accelerators that are being integrated, we think, yeah, simply there will come a point in time where there's no other option but to utilize hybrid bonding to scale these systems further without increasing the size substantially. So I don't know, is that 25 like I show on the chart here, 26, 27? Not sure, but I'm pretty sure it'll happen. So that brings us to the equipment side. So Besi, we've recently introduced a new hybrid bonding system. We call it the 8800 Cameo Ultra Plus. So the Cameo 8800 Cameo equipment platform is kind of a mature equipment platform already. Besi, we're using it for standard flip chip, for thermal compression bonding, and other things. But we've adapted it and heavily customized it, I would say, for hybrid bonding. And we call that system the Ultra Plus. So we have integrated a new bond head with a very unique vision technology, and also modifications to the bond head to improve the precision and reduce the sort of the errors that we can see in other kinds of bonding technologies. We've done a number of other things in the system, but the end result is that we have been able to achieve sub 200 nanometer accuracy on these machines in a very stable way. And at the same time with relatively high speed given the accuracy. So dry cycle speeds in excess of 2000 UPH. And as I mentioned earlier, we really had to re-engineer this whole machine for cleanliness. So when you look at it from the outside, you see a different cover design. You see in the front of the machine some different kind of venting and air handling unit on the back. There's a number of changes on the inside of the machine as well that helps to prevent the generation of particles during the movement of all the bonding systems within the machine. And then as well, these things have to be integrated in front-end wafer fabs now. So for the most part, hybrid bonding is done not in kind of OSAT back-end factories or IDM back-end factories, but kind of in a front-end environment in foundry or at least IDM fabs. And that also requires not only cleanliness, but also high levels of automation. So all that's been implemented. We started shipping and production in Q1. We're now shipping as well highly integrated systems that include multiple bonders, as well as the integration of the plasma and wet clean and some other functionality um, in an integrated line to improve the productivity and increase the yield um, of these systems. And this is really desirable for customers that have complex multi-chip um, designs that require, multiple different types of devices to be bonded. They want that to be done in a very controlled environment with very good control of queue times and things of that nature. So we've shipped our first systems already with this configuration with our partner Applied Materials. And we're working now on further improving the system. We've demonstrated in the laboratory already sub 100 nanometer placement accuracy. Not yet shipping on production machines, but it's been demonstrated. So we have a proof of concept and a very concrete way to bring that to fruition in the market. So I would say that by the end of next year, all the machines that we ship will have this capability of sub 100 nanometer. And why do we need to do that? So today, the application that I showed you is at a 9-micron pitch. But we have applications in mind, and people are talking about 3-micron pitch and even 1-micron pitch in the future. And to really achieve those things, we need 50 to 100 nanometer accuracy. Just a few aspects of this bonding system that are unique. The first is the bond head system itself, which has been heavily adapted and customized for hybrid with different air bearings and different tool holder designs, optical elements built into the tool holder. We have a new multi-camera vision system we call Van Gogh because we're a Dutch company. And then all this is built on our dual gantry system. So you can see here in our systems, we have not one, but 2 bond heads that are independently moving. So we can have some level of parallel activity happening within the bonder to increase the throughput. And as I mentioned, the cleanliness is taken to the next level. So we have integration with EFEMs, and we have a lot of modifications within the machine to manage, prevent, and then manage particle cleanliness inside the machine. And maybe I can show you a video here. Serious-on, I'm not sure if this video is showing well, but basically what you're seeing is a single head operating in the bonder. Remember I said there's two heads, but I'm showing one in operation here. And doesn't look like much, but there's a lot happening during these movements to very precisely achieve that alignment at the sub 200 nanometer accuracy. But you see it's very fast actually. And then as I mentioned, we have a close partnership with Applied Materials. So you can't do hybrid bonding in a vacuum. You need to have all of the upstream processing well understood, from the creation of the bond pads to the preparation of the surfaces and so on. And for that purpose, we partnered with Applied Materials. They're working on all these other steps besides the bonding, and they're collaborating with us on this whole process integration. And to facilitate that whole collaboration, we have a Center of Excellence in Singapore, where we have a line set up with all the capabilities that we need in terms of processing as well as FA. And that's been quite productive in terms of bringing the process development to the next level. All right, so with the remaining 5 minutes, I just want to hit on a couple of other technologies that are complementary to hybrid bonding. So as I mentioned, hybrid bonding is great, but if you can't connect the hybrid bonded chiplet to the rest of the world, you're in trouble. So One of the technologies that helps us is TCB, thermocompression bonding. This is really helpful for very fine pitch, but not quite as fine pitch as hybrid. So I'm talking in the 20 to 40 micron range. This is an example of very high density memory stacking using thermocompression bonding. For these applications, we're introducing a new platform, the 9800 TC Next, which is a chip to wafer thermocompression bonding system with about half a micron placement accuracy, so still very fine accuracy, with controlled atmosphere environment and even fluxless capability. And this is really targeted at chiplets that don't require hybrid necessarily, but either require the assembly of a hybrid chiplet to the substrate or just two fine pitch chiplets together on the substrate. So this is coming to market in Q1. And then another use case or another kind of layer in the interconnect hierarchy for these chiplets is bridge die or fan out die. And this is typically used in the cases you see on the left of a fan out interposer as an example, where you have a molded wafer with embedded chips, and those embedded chips can be bridge die or local silicon interconnects, as TSMC would say. These need to be placed with very high precision in a die face up or face down configuration in a fan out kind of a process flow. So it requires high precision chip to wafer bonding, but in a face up orientation typically. This is being used in high volume production now. A couple of high profile announcements, this AMD product that uses the elevated fan out bridge, as AMD calls it, and then the M1 Ultra also using a similar technology. And basically it allows a very high bandwidth 25 micron pitch interface between chips that are mounted on top of this interposer. To enable this application, we've introduced a new system we call the Cameo Ultra. And basically this provides the ability to place die in a face-up configuration onto a substrate with sub-micron accuracy as well. And we do that with another new, really innovative alignment system that uses a clever method of recognizing the location of the die front and back at the same time without slowing down the machine. So we can achieve a 5,000 UPH sub-micron placement die face up, really optimized for fan out and bridge attach. And this kind of shows that working. Here you can see the dual gantry system. And you can see here the flip systems happening on the bottom. I think I'll leave it at that. In the interest of time, we'll move on. And then at the end of the day, we have typically a need for high precision flip chip attach for mass reflow kind of interconnect systems. These typically don't require quite as accurate placement. So something in the range of 4 micron is adequate. However, speed and cost of ownership is really critical. So for these applications, we've developed a new system that enables us to pick 4 die from the film frame in parallel and then place.
Oh, good. We have, this has been a very.
I think, yeah. So this is called the Flip Chip Quantum HS, and this is has been shipping in production now for quite some time, achieving speeds up to 20,000 die per hour in production. We're also working on silicon photonics. So going back to this image that I shared at the beginning, you know, there's many companies working on photonic chiplets. Air Labs is one example, ASC showing an example here, but basically the requirement here is varied, but generally requires integration of a PIC and a ESC and a way to bring the light to the photonic chiplet. So these are all applications that we're working on as well in parallel. And then for all these applications that require wafer level assembly, at the end of the day, we need a way to encapsulate the wafer. So for this, we are offering a wafer level molding system. What we do a little bit differently at Besi compared to what most people are used to is we employ transfer molding. And the benefit of transfer molding, especially for these kind of applications like hybrid bonded chiplets, is that you can do exposed die molding at the wafer level. So you can expose the backside of whatever you just mounted to the wafer during the molding process. So this is something that's also available and being used in R&D. And then just a reminder that we're also supporting the back end of line assembly. So once we've done all this fancy front level interconnect, high density interconnect, we also can support, strip based molding and wafer level molding, as well as singulation and trim and form. So the last thing I wanted to touch on is ESG. This is a really serious topic at Besi. We commissioned a study to look at, where is energy used in the life cycle of our products, the whole life cycle, not just the production of our product. And one of the things that we found is the energy used in the operation of our machines and our customer sites has the biggest impact on the carbon footprint of our machines, more than anything else. So this is where we're spending a lot of energy to optimize the energy performance of our machines to really reduce the carbon footprint as well. It has the side benefit of also reducing cost of ownership as well. But the motivation is really to reduce the impact that we're having on the planet. And with that, I'd like to wrap up. I'd like to thank the funding agencies that help to make, or programs that help to make a lot of this work possible. And Surya-san, I have a few minutes for questions. And I'd like to thank you again for inviting me to talk. Yeah.
Thank you very much, Chris. I'll ask Wikis to lead the Q&A sessions. Wiki.
Oh, thank you, Chris. Excellent presentations and very in-depth sharing about the capability that Besi has, and really looking forward for all the good work that's been produced to enable advanced packaging that we have in the roadmap. We have a series of questions already typed in the chat group, but I'm going to pick a few and then we can go through that. And at the end, we'd like to ask you a separate questions that regarding Besi and iNEMI. Is that okay, Chris? So yeah. I think a few of the questions, if you can look through the chat, but you can see that one of the questions is about reliability suffering, about this hybrid bonding, right? What is the test protocol being used to assess the reliability of hybrid bonding?
Yeah, I'm sorry, I'm not seeing the.
Oh, maybe I'm reading up. Yeah.
No, that's okay. I understand the question. The question is what are the methods used to assess reliability of hybrid bonding?
Yeah.
At a first level, they're all the same tests that you would do on any other semiconductor package. So people are using, all the JEDEC test methods that are used to qualify a semiconductor package. So that includes, temperature cycle, temperature humidity bias, things of that nature. But in addition to that, there's been some really good research done and papers published on understanding the moisture sensitivity of hybrid bonded products. Is the interface really hermetically sealed, and is it as reliable as a flip chipped and underfilled structure? There's also been quite a bit of work done on chip package interaction, and based on what I've seen, the initial conclusion on some of those questions is that because you're bonding these passivation layers directly to each other, and there's virtually no CTE mismatch. The
Mhm.
hybrid bond itself is really quite structurally reliable and
Mm.
liable against moisture ingress and so on.
Mm.
I would refer you to a very good paper from ST at the Minipad conference in Grenoble that was done in June this year that addressed some of those questions.
Great. Thank you very much. So as you developing all these machines, right, as assembly machines and so on, is there a standard article or samples for you to make use of that to evaluate your tool performance and the scalability of the hybrid bonding?
No.
No, so you leverage samples from customers and
Yeah,
for the
so
development.
I'll give you a little more color. So that's one of the reasons that we have partnerships and we have collaborations because we don't make devices. So one way that we get our hands on material is by engaging with customers, certainly, but then we also have two other avenues. One is our collaboration with IMEC in Belgium. So IMEC is a well-known research institute. We shipped one of our bonders to them, and they have test vehicles, which we have some input on in terms of the design. The other is with our collaboration with Applied Materials in Singapore and their co-location with iNEMI. We can actually create our own test vehicles there. And that's what we've done. So we've created some test vehicles that are useful to us. They're not openly available. They're still kind of in this closed ecosystem, but we do have some capability to do that. But I would say that we always rely on customer material to fully evaluate the process because any of these test vehicles are so inherently limited in the data that you can generate. Yeah.
Thank you. A few more questions. Maybe I just pick a few. Like, what kind of cleaning is done and after the dishing, I would say, right? Before the hybrid bonding, kind of cleaning needed.
Yeah, well, I can't really comment on the detailed flow there. I would say that after CMP, there's different strategies that are used, different chemicals used. And each of our customers has a little bit different process integration, I would say. We have a baseline process in our Center of Excellence in Singapore. With just before the bonding process, we do an aqueous clean. But prior to that, there could be other methods used as well.
Okay. Going back to the reliability question, do you see any gaps in how we assess the reliability of the hybrid bond, or there's no gap at all?
One gap, I think one of your questions will be how can iNEMI help? One gap that we see. One gap that we see is we don't have a good way. The industry doesn't really have a good way of evaluating the bond strength for die to wafer hybrid bonding. So in wafer to wafer hybrid bonding, there's kind of a way you can do that. You can drive a wedge in there and pry the wafers apart and measure the energy it takes to do that. Die to wafer bonding, that's more difficult to achieve. So I would suggest for iNEMI that would be a logical things that would make sense to work on.
Yeah,
I think that's the biggest problem that we face at the moment.
I see. No, if we can pull the resource together, will iNEMI access to the samples, like potential samples that that Besi can provide? Is there something that can be
I
done?
think we can talk offline about how we do that, but I think we
Mm.
interested in, I don't know how iNEMI works exactly, but I imagine you have a program that you put together, a working group, and
Yes.
multiple companies kind of get together and talk about which
Yes.
things can contribute, right? So we're
Yes.
open to supporting that.
Mm-hmm. All right. Great. So maybe the last questions, right? I mean, in iNEMI, we talk about some low temp solar applications for first level interconnect. Where do you see the applications of this? And do you get requests on evaluating this low temp solar for first level interconnect, especially for those device that is more temperature sensitive?
Yeah, I mean, obviously that's where we would see the need.
Mm-hmm.
And of course, with hybrid bonding, we don't have solder, so that helps. But for thermal compression, we're, I think with IMEC, we have a thermal compression bonder at IMEC, and they're definitely using that bonder for evaluation of low melting point solder, different metallurgies.
Mm-hmm.
And as you mentioned, it's typically for temperature sensitive devices like certain memories.
Mm-hmm. Yeah, and photonics devices.
Also be photonics, yeah.
Yep. Mm-hmm. All right, I think that's all the time we have for Surya-san. Anything that I miss out?
Yeah, I'm just wondering, since we have several more questions, Chris. So I think you can access to the Teams after these sessions, right? Then if you have a times, then access to it, then as possible as you could, would you answer some questions, or
Unfortunately, I have
think,
to
Chris?
close my laptop and go to the airport immediately after this.
Okay.
So
Yeah, I
I
think we
apologize
can
for that, but
wait a bit later.
a couple of things I'd like to point out. I'm pretty friendly and willing to accept LinkedIn invitations. So anybody that wants to contact me that way is welcome to do that.
Okay.
And
Yeah.
if you would like to, Surya-san, if you want to, maybe share in an email or something like that,
Yeah.
the questions, and I can try to help to answer some of them.
Oh, great. Thank you very
Great.
much.